No.
Okay, and Felix, can you confirm you can see my first slide?
Yes, totally.
Brilliant, good. Okay, well, good afternoon, everybody, and thanks so much for inviting me. It's a real honor, actually, to be invited to talk to you today. And of course, this is one of the few upsides of COVID, is that we're all visiting each other's labs much more than we would otherwise, because we can do it all virtually. And so, you know, I'm glad that we're all taking the opportunities to invite people to talk to us, which we would otherwise perhaps not do. So yeah, what I want to talk about today really is I'm basically looking to the future, which hopefully is something you're quite interested in. And it's all about spoken language technology. And as you see the title, I mean, basically, as I'm about to show you, I mean, spoken language technology seems to work, right? It's amazing. The deployment of modern speech recognition, speech synthesis, it's out there, it's being used, it's quite amazing. So maybe we're done, right? Maybe there's, you know, the research is over and we can just all go and celebrate. And indeed, you know, progress. Oh, yep, good, okay. Progress has been amazing. So you just heard, my history goes back quite a long way. So I've actually had the huge pleasure of being able to see a field which, you know, which started off not being able to do very much. You know, when I started, the speech recognizers could only recognize 10 digits and couldn't even do that very well. But some of those early systems did find, you know, a way into being used, and particularly in the military, command and control systems didn't require very big vocabularies at all. And we're taking advantage of, you know, hands-free, eyes-free control of equipment. But then it wasn't long after that we saw the appearance of dictation systems. So I don't know how much history you know of the field, but it was in 1997, when we had a big paradigm shift, and it's when products like Dragon Naturally Speaking came on the market, and suddenly it was possible to dictate documents using your voice into your PC. And a lot of technology, a lot of interesting algorithms had to be developed, some of which I was involved with, to allow that to happen. And we moved from sort of very simple command systems where you had to pause between the words to suddenly being able to speak whole sentences. And we had the algorithms that could cope with that. Then we had the era of interactive voice response systems, where we're having these annoying telephone-based systems which were trying to use speech recognition, for example, and speech synthesis to provide services, basically annoying the entire population of the countries where these things were deployed, as people were trying to get through to their gas company or something and were faced with some awful telephone-based automated service. And then again, we had a major shift when voice-enabled personal assistants came along, particularly when Siri arrived in 2011, followed by a whole bunch of other things similar to Siri, and then culminating in 2014 in the appearance of Alexa and Amazon Alexa, and basically putting speech recognition and synthesis into people's homes, not just on people's phones, but into people's homes. And of course, what's going on now in the research labs is people are looking at things like embodied conversational agents. These are, you know, virtual characters which are going to converse with us, and ultimately, what I like to call autonomous, excuse me, social agents or robots. So this is sort of rough timeline of how things seem to be going, and we're in the middle of this right now. So progress has been amazing, and particularly things like automatic speech recognition. There's been, especially in the last sort of 10 or 15 years, there's been what I like to call the word error rate wars, where all the big companies, Microsoft and Amazon and Google, have been sort of slugging it out, claiming and counter-claiming that they've got the best speech recognizer and the lowest word error rate. And it's just been going on and on and on as they slug it out. But the reality is that the error rates have been improving. And so that's been very, very impressive. So that's what's been going on in sort of research labs, and in the real world, we've actually seen the technology getting out there. As I mentioned a moment ago, it's going into people's homes, and the numbers are phenomenal. So these are a couple of years old, but tens of millions of Alexas sold worldwide over Christmas in 2017. Google Assistant on huge numbers of devices, and Siri has over 40 million monthly users just in the US. I mean, this is absolutely incredible. I find that very difficult. You know, this is, for me, has involved pretty near the start of this stuff. One could hardly imagine that this was going to happen. So let me just summarize where I think we are in the state of the art spoken language technology. So one thing that's been true over the past many decades now is there's steady year-on-year progress. And this has been a very, very good thing. I mean, it's just been continuous improvements in all aspects of the technology: recognition, synthesis, dialogue, everything. So why is that? Well, you probably know the answer here. But you know, one of the things that shouldn't be underestimated or underrated is, of course, that just the sheer power of computers these days compared to what was available 10, 20, 30 years ago is phenomenal. There's more compute power in your pocket now, in your phone, than most research labs could dream of 40 years ago. So that means we can compute things that we kind of knew how to do, but couldn't dream of actually running the programs. But also, of course, there have been significant developments in machine learning. One of the real pleasures of being involved in spoken language research, spoken language technology research, is that it's always been at the forefront of machine learning. From many, many years ago, we've always been using the latest machine learning techniques because speech is such an interesting and hard problem. And that continues to today. And the other reason that we're getting huge improvements recently, of course, is that we're now getting access to not only very, very large data sets, but those data sets are coming from real world usage. And this is why the companies, of course, are becoming very powerful, because they're the ones who actually have access to all this. In fact, it's getting quite difficult now for universities to get access to sufficient training data to do their research. And then the final thing on the list there is that our field has been heavily assessed. There's a whole community which has been concerned with this for a very long time. So we benchmark test things. I mean, in the early days, nobody shared corpora. There were no standard benchmarks. So people would just publish papers and say, oh yeah, we got 98%. And there was no way of knowing whether that was good or bad. You didn't even, didn't know whether that was an easy test or a hard test. That all changed some number of years ago now, and our community's been absolutely fantastic at benchmark testing. And I think you had a talk from Bjorn Schiller just recently, so he's been championing one of the he's been running all these challenges, and lots of other people are doing similar things. And so that means we really know what works and what doesn't work. So that's also a very, very good thing. I shouldn't spend too long on this, but it is interesting history here. Now, this is a statement which some people find hard to take. So progress has not come about as a result of any deep insights into what you and I are doing when we're talking to each other. Now, whether that upsets you or not, or maybe you just don't care, I've put it as neutral because, it depends which community you're in, really, as to whether you think that's a bad thing or a good thing. And if you want to ask about that, we can come back to that, but I'll give you some hints as we go along anyway. Now, here's some reality I want to introduce. It is expensive and difficult to port our current solutions to new applications and to new languages. And part of the reason for that is because of these enormous data sets. And so there's the sheer cost of collecting such a data set and then retraining all your models, which might take weeks or months on some high-power computing array. That's an expensive business. So that's not great. There's something not quite right there. And also there is beginning to, now we've got real-world systems deployed, we're beginning to see some interesting effects in terms of usability. And usability appears to be an issue. So what I'm going to do in this talk is focus on these two items. Going to spend more on this one, and hopefully we'll have time to deal with the second one as well. Excuse me. So what's all this about the amount of data? Well, I actually did some work myself quite a few years ago now, almost 20 years ago. And I asked a rather obvious question, which nobody else seemed to have asked, which is, how does performance depend on the amount of data? Particularly, this is for automatic speech recognition. So the graph you see here, the vertical axis is word error rate, which is how we normally plot performance. So high is bad and low is good. And how does that depend on the amount of training data? That's a reasonable question. But what I was asking is, well, how much training data do we need to meet our application requirements for certain levels of performance? So what levels of performance might be we want to target? Well, there's an obvious one, which is human abilities. So human speech recognition is not perfect. It is pretty astounding, but it's not perfect. And on this particular task, which is a sort of large vocabulary transcription task, then human performance is of the order of 2.5% word error rate. And so you might think, well, that's a reasonable target. But why do we think that meeting human performance is a reasonable thing? I mean, in fact, for any application, we should be worrying about what the application requires, not necessarily what a human being can do. But it turns out for this kind of transcription task, that a usable level of performance, and I did some separate research on this and modeling, is about twice that. It's sort of more like 5-6% word error rate, which is, as you can see, still quite a long way off of what was feasible at the time that I did this study. But what I was interested in was what happens if we extrapolate this data, and to find out how much training data we need. And I did this, and I came up with, as you can see, some pretty large numbers. Now, when this work was done, I used to give this talk, and people were either completely gobsmacked, what's he talking about? 100,000 hours or 1 million hours of training data. It seemed totally unreasonable at the time, but not today. Current systems are indeed in this region. And in fact, here's an ICAS paper of a couple of years ago, lessons from building acoustic models with 1 million hours of speech. So in that sense, you say, okay, great. We're now in an era where we can collect that amount of data, and we can build our models, and we can get to usable performance. So problem solved, right? But you have to ask yourself, well, hold on. 1 million hours of speech? What is that from a sort of an ecological point of view? What does that actually mean? And this was the point of the paper that I'm referring to here. So let's look at this graph in a different way. How much speech has a 2-year-old heard? Well, it's about 1,000 hours. Now, your 2-year-old child, if you've got any siblings or know any 2-year-old children, you realize that their language ability is not great. They're engaging in language, but they're very unlikely to get a 2.5% word error rate on a large vocabulary transcription task. Okay, fair enough. So our systems are nothing like a 2-year-old child, but a 10-year-old child has heard about 10,000 hours. Now, a 10-year-old child is actually pretty much at adult levels of performance. A 10-year-old is fully engaged with language, is incredibly accurate at perceiving speech. And that's 10,000 hours, not 100,000 and not 1 million hours. So what is 100,000 and 1 million hours? Well, that's pretty much more than a lifetime. In fact, it's multiple lifetimes of speech. At which point you might want to think, I mean, you could take the view, well, fair enough. If that's what it takes, that's what it takes to build one of our automatic systems. But it doesn't feel right, does it? It's not very parsimonious. It seems inefficient in the extreme. We know that a human being can get away with 10,000 hours, 2 orders of magnitude less to perform at a level way beyond what we need for usable systems. So we have an issue here. And so I want to address that issue now. So where do I think that the problem comes? Why are we so inefficient? Well, this is actually traditional spoken language processing architecture. You may have seen this actual diagram. It's the W3C standard. And it seems on the face of it very uncontroversial. I mean, you've got the user on the left, the application stuff on the right. You've got the top line running from left to right is the speech recognition with language understanding. Then we've got a dialogue manager, and then we're coming along the bottom, we've got language generation and text-to-speech synthesis. Well, I mean, how could you possibly argue with that? What's wrong with it, you know, if anything with that? Okay, well, I'm going to say it's basically everything's wrong with it. This is a classic stimulus response, or to put it another way, behaviorist view. This is a word from psychology. And it's actually taking a particular stance about what language is like. And it's a very conservative and restricted stance as to what language is like. And therefore, you know, I'm claiming this is really holding us back. So what is language like? Well, the behaviorist view is that language is a bit like a game of tennis, right? People are taking turns and they're just passing messages backwards and forwards, you know, and it's simple as that. And all we have to do is interpret the messages and we're in business. That, from a linguistics or a linguist's point of view or a psychological point of view, or for the more modern view of language, is not at all what language is like. Language is more like this. So this is a three-legged race here. So you've got people running together, but their legs are tied together. Two of their legs are tied together. And this is this requires very careful coupling, and it's continuous. And so this is thought to be a good analogy of what language is really like, where when we engage in language-based interaction with another partner, it's more like this. It's not about just passing messages. It's about intimate, coupled, engagement between the parties. So at this point, I could turn this into a sort of six-hour tutorial on how to go about modeling all this. And I just draw your attention to the fact that I've published a number of papers developing various architectures which are sort of becoming more mature as they've developed. And they've had various names. So there's presence in the middle there, predictive, sensory motor control, and I forgot what the E stands for. As you can see, that's published more than 10 years ago. And the current one is a needs-based architecture. I'm going to talk more about that. But rather than just throwing these architectures at you, I want to actually take you through just some logic as a way of thinking about what's going on when people are interacting. And I'm really going to go back to some extreme basics. Okay, and I'm going to start talking about things which are a long way now from language, because one of my hypotheses is that our view of language is missing something fundamental, and that is that the foundations on which language is built. That is, we don't have a theory of interaction. We don't have a theory of information-based interaction between any organisms, which is why I'm very interested in what animals are up to. Anyway, we'll come to all that. Let me just take you through this sort of logical series of premises here to get you up to speed on what the latest architecture, I think, needs to look like. So we're going to be looking at a sort of conceptual framework, and it's all going to be about intentions, actions, and consequences. And most importantly, we're going to see loops behaviors. We're going to see closed loop behaviors. Right. Now, I said I'm going to start with some basics. So here we are, right back at the modeling the physical world. So here we've got the world is basically a transform, F of W. So there are actions in the world, and actions are transformed into consequences. Okay, so this is just physics. And that's a continuous loop. So those consequences become the next actions, if you like. And so the whole thing just cycles round. It's a continuous cycle of cause and effect, as I say, just physics, but we need that to get us started. So now I'm going to throw an agent in. So now we've got an agent interacting with the world, and the agent has intentions. So there's the agent on the left, there's the world on the right. So the agent has intentions. The agent is going to initiate some actions, which of course the world is going to transform into consequences. So given that the agent has certain intentions, how do they get the right consequences? Well, at the moment, we've got two transforms. There's what the world is doing, and then there's the agent has to transform their intentions into actions. So that's the second transform. So this is only going to work if we know what G is. Well, where's G going to come from? And that's going to take a lot of trial and error to get G right? And this is open loop stimulus response. There's that. There it is again. Behaviorist configuration. Right? Now there is, of course, a solution to this, which is we use an inverse transform. So G becomes the inverse of F of W. This is brilliant, right? This is guaranteed to work, right? We've got the intentions. They will be transformed into actions, the appropriate actions, and that will be transformed back into consequences. Still open loop, and it's using an inverse model. But where do we get this inverse model from? And I mean, this is basically an inverse model of the entire world. And I mean, you know, this is, and it has to be right. It can't be, you know, it can't be miscalibrated. It's got to be absolutely perfect for the consequences to match the intentions. So that's a big, big problem. And learning an inverse model in this sense is going to be really, really difficult. Or how to calibrate it, it's going to be really difficult. But there's another solution, which is not to have an open loop configuration, but to have a closed loop configuration. And this is so obvious that a lot of people completely overlook this. So let's have the agent pay attention to the consequences of their actions. Duh. So they're observing the consequences, and they compare the consequences with their intentions, and they have a controller. If the consequences don't match the intentions, then that determines the actions. And essentially this closed loop arrangement will converge, or the idea is to set it up so that it does converge. So this is what's called a closed loop negative feedback configuration. And the beauty of this is that whereas the previous arrangement with an inverse model, if we had an arbitrary disturbance in the world, of course the inverse model wouldn't know anything about it. And so it would just do everything wrong. Whereas in this closed loop arrangement, any disturbances in the loop in the world there will be automatically compensated for within reason. I mean, you know, it has to be within the bounds of possibility, but closed loop negative feedback control structure has some very interesting stabilizing properties. This is actually homeostasis, which is a property of all living systems. He throws in. Okay, now I'm going to add another little layer here, which I'm not going to come back to, but I just want to point out that within this control structure, the intentions are compared to the consequences. That can be just a subtraction process. So if the consequences equal the intentions, the error is 0. But if they don't, then the error is large. That error signal we can think of as a kind of emotional valence. In other words, error signal of 0 is great. That means that agent can feel happy. Whereas if the error signal is high, then it's unhappy. And I'm just throwing that in there because I also want to point out that the controller has to take that error signal and initiate the actions. Now, the controller can apply more or less effort. And in a classic control system, there is a parameter for exactly that. And it's the loop gain. And I'm just going to point out that this is like, has a sort of psychological interpretation of motivation or effort. So suddenly with this very simple structure, we've got an agent that cares about what it's doing and is going to feel unhappy if it's not achieving what it wants. even in this simple configuration. Okay, I need to move along very quickly now. So that's a controller, which in an engineering sense would be a motor of some kind. But we're computer scientists, aren't we? So let's turn that into something we closer to our home, which is more of a search. So we're trying to find the actions which will close the loop. So the motivation or the effort now becomes depth of search. And if we have a superficial search, then we're not going to perform as well as if we have a deep search, for example. So again, I'm just throwing that in as a to give you connections with other things that you may already know about. So that's all great, but what if the agent can't detect the consequences of its actions? What if it they can't be observed in space or in time? Now you might think, well, that's making life very difficult. Why is he saying that? Well, that's precisely because I'm racing towards speech and language, right? So when you're speaking, you're assuming that the listener is doing something with your speech, but you can't observe that directly. So this is going to be now quite important to the next step. So we can overcome this by having the agent estimate the what's going on in the world and still having a closed loop, but it's essentially an approximation. So there's an approximation to the F of W transform, there's approximation to the consequences, but the loop still functions. And it may still work if there are disturbances, if the disturbances are perceptible. And so basically we've now got an approximation to this external transform, and we're making an approximation to it. And it's an estimation of a forward transform, and forward transforms are actually much easier to estimate than inverse transforms. That's an estimate of the consequences. Okay, so we put the loop inside the agent. Right, change of gear. So forget the agent that's trying to control the consequences. We've now got an agent interpreting the world. So we've got an agent on the right now. So the agent is observing consequences of actions, but what the agent wants to do is to figure out what the actions were. What's caused this? I'm observing this in the world, but what's caused it? And hopefully you're getting a feel for now why I'm looking at things in this way. So there's some transform in the agent, which is estimating, which is some approximation of the actions that it can't directly observe. Okay, so inferring the causes of events. Right, so there is a way of doing this. Surprise, surprise. It's an inverse transform. We can do it perfectly. Okay, so all we need is the exact inverse of F of W. Sounds familiar, right? And we're guaranteed to do the right thing. But if there's noise and disturbance, blah, 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 that isn't going to work. So we need to move on from the inverse transform. So what we can do, though, is have an estimate of the forward transform and then do a search. Okay, so this is a sort of model-based inference process, which should be familiar to you, hopefully by now, as a standard approach, inferring the causes of events using a forward model. And this is an approach, by the way, that's been used in speech for many, many years. And so the key thing is you've got to get that transform, estimate that forward transform. And again, forward transforms are much easier to estimate than inverse transforms. Right, so let's put these two together now. So we've got an agent communicating to an agent. So we now know that we're not going to do it using inverse transforms, but we've got a receiver, we've got a sender. The sender is going to estimate the transform of the receiver, right? So it's inferring the interpretation by the receiving agent in order to determine its actions, what to say. Okay, and that is termed synthesis by analysis. Okay, synthesis by analysis. Right, the listening agent or the interpreting agent, same deal. We've got the transform in a search process. So the receiving agent is inferring the communicative intentions of the sending agent. So that is the transform that's being estimated. And this is analysis by synthesis. So the previous one was synthesis by analysis. This is analysis by synthesis. Okay. Right. So there we've got two agents, each with a model of the other. Well, that's great, but where do those models come from? How does an agent have a model of another agent? That sounds like a complex calibration process. Well, there's a way to bypass this, because both of these agents, in some sense, are similar. They're both communicating agents. They have the same structures, essentially. And so we can cheat. Cheat's not quite the right word. We can come up with a clever solution here, which is that we replace those transforms, those estimates, with another inference based not on the other agent, but on self. In other words, the agents are using knowledge of their own abilities to interpret the behavior or to influence the behavior of the other agent. This is a really important step. Agents exploiting knowledge of themselves to model each other. Now, you might think that's a bit extreme, but there is a lot of neurological evidence to suggest this is exactly what goes on. So we get a warm feeling here. All right. So let's take this simple-minded model and just talk about one agent for the moment. So obviously an agent is generating behavior and also inferring, has perception. So we want to put the two together. So we've got the intentions of self generating behavior through a production process using the structures we've just seen. At the top and at the bottom, we've got the perception, which is the inference, where they're determining the intentions of the other agent from observations, again, using knowledge of self. So that's fine, but we've got these, where do these intentions come from? We're sort of missing something quite important here. And I've been sort of using this term all the way through, but where do they come from? Well, I'm going to step right back. By the way, you notice, this is a talk about technology, but pretty much I'm talking about models of living system behavior. I hope that's clear. Which is my excuse for jumping right back to this, because there is an ancient model here of why does a human, somebody asked the question a long time ago, why does a human being do anything? Or why does a living system do anything? And the bottom line is a set of needs. And so Maslow, way back in the 1940s, put up this hierarchy of needs for a human being. And you can see that basically at the bottom there, you've got the absolutely fundamental physiological needs. So without those, you don't survive. And that's common across all living systems. And then as you go up, you get more and more sophisticated needs. Now, it doesn't matter what's in here, really. The point is to identify this notion that there are fundamental needs that a living organism has. By the way, there's been an update to this model, which has been going around the internet. Then there are needs which are even more fundamental than physiological needs, especially these days. And that's Wi-Fi. We couldn't survive without it. So let's then talk about, wrap this all together very quickly into what I like to call a needs-driven, an awful acronym, MBDIAC agent. Where MBDIAC stands for mutual beliefs, desires, intentions, actions, and consequences. So I appreciate there's some words there I haven't talked about at all, but there's only a limited amount of time. But hopefully what you can see in this structure is some familiar elements. So we've got on the extreme right, the production and perception elements that I talked about, but that's driven by intentions, as we saw. But then we've got a similar structure, one step back, driven by desires. And then a similar structure again, one step back again, driven by needs. And so we've got this very sort of beautiful symmetric arrangement here to model an agent, which is capable of formulating its behaviors in order to meet its needs and of interpreting another agent's observed behaviors to figure out what they're doing and why, and essentially saying, if I was doing that, then the reason I'd be doing it is this, and that must be the reason this other agent is doing it. So I can't go into a lot more detail, but I'm just going to give you some experimental support in a sec. But you can read about that if you're interested. There's a paper in Frontiers not so long ago, excuse me, which is towards a needs-based architecture for intelligent communicative agents, speaking with intention, sorry. Yeah, okay, so there are a bunch of implications, and I'm just going to focus on one, which is the implications for speaking. So there's various points here, which is that there are some aspects of behavior, and in particular, and speaking is just a behavior, which are often completely overlooked. And especially if you look at the speech synthesis kind of work, there's a sort of assumption that we're just translating a code into acoustics. And that's the classic stimulus response behaviorist kind of static view of things. The reality is much more interesting and dynamic. Signaling involves effort. So you can make very, very clear signals, but you're going to use lots of energy. Or you could, if you can't be bothered, then you use much less energy and you put all the pressure on the receiver, and the receiver's now going to have a hard job. And this dynamic control is typical of all kinds of behavior, and it's especially true of speech. And the reference there to Björn Lindblom, a Swedish phonetician who pointed this out many, many years ago in his H&H theory, hypo and hyper theory, showing how simple control structures could explain the range of pronunciations from a mumble through to clear speech. And it's still very, it's well known, but people don't seem to take much notice of it. And I'm very surprised, because to me, it's a fundamental property. And the other thing, the point I wanted to make is that a lot of people working in speech synthesis particularly are very interested in the signal that's generated, but it's not about the signal. The target for a producer of a linguistic communication is the perception, and it's not perception at a low level, it's perception at a high level. It's for achieving a contrast at what I call the pragmatic level. In other words, for getting the person, if you're trying to get the person to do something, it's whether they do it or not that matters. It's not the phonetics, it's not the acoustics. All that follows. And the optimizations that are being performed, the search that I'm identifying in the architecture, therefore is over competing perceptions at these high levels, not over competing signals. And I mentioned disturbances. Well, disturbances are like obstacles, things that have to be overcome. And that's the beauty of a closed loop control structure. It can overcome obstacles in a very parsimonious way. So what are the obstacles? Well, when you're speaking, the obstacles are people misunderstanding what you're saying, alternative interpretations, not just misrecognizing, but misunderstanding. That's the really important thing. And of course, competing signals, anything else which might get in the way, it stops you hearing, essentially. So I'm going to give a little example here. I think I've got time. How am I doing? Yeah, just about. This is a phonetician.
You're very welcome to speak as long as you like.
As long as I like.
Yeah,
all right. Well, okay.
I think it's pretty fascinating. Yeah, take your time, really. Take your time.
Bed down for the evening here, folks. So this is Sarah Hawkins here, who's a professor of phonetics at Cambridge University, a colleague of mine, who's got this wonderful example. So the context is, she's at home, and she's sort of sitting in her living room, and her husband comes in and says, "Where's the newspaper?" And so she doesn't know where the newspaper is, but depending on the context, all kinds of possible responses could occur. There is no fixed signal here, no fixed response. This dialogue system is much more interesting and complicated than you might be led to think. So, for example, if the TV's on loud, or there's a workman right outside the window drilling, so there's a significant competing signal, then she might reply, "I do not know," in order, if she cares, by the way, assuming there's a sufficient motivation, right? But we've got this range of possibilities. I do not know, I don't know, I don't know, don't know. Or if it's very quiet, And she doesn't care very, is not highly motivated. So the husband says, "Where's the newspaper?" And the response is, 3 nasal schwas. But it's perceived, it's heard as "I don't know," right? It's not perceived as 3 grunts. It's perceived as a linguistic expression of not knowing. This is really important, I think. Okay, so so much chit chat about the principles. Let's show you a demonstration of stuff that actually works. So this is Mauro. He's one of my ex-PhD students, and he did his PhD on this. And what he was doing was trying to come up with a speech synthesizer which had the properties that I've just been talking about. In other words, a speech synthesizer that knows what it is saying, is listening to itself, and making a judgment as to whether it's achieving its perceptual targets. And if it's not, it will adjust its pronunciation, just as you and I do. So, right now I'm hyper-articulating because I'm trying to communicate, with you guys, putting in lots of effort, which, means afterwards I'm going to be quite tired. And this is a natural adaptation. So could we have a speech synthesizer which does this? Well, this is Mauro's model. It's called C2H. And I'm not going to go through in great detail, but just draw your attention to this is the feed-forward path, which looks like a conventional speech synthesizer. There's nothing very surprising in there. But there's all this stuff on the right, and this is the feedback path. So this is where it's estimating the consequences of its actions, just as I described as I went through the sort of principles earlier. And you can see that this structure has got its fingers in the forward path and is going to make adjustments. So here are some results, so we've got various measures here. So the synthesizer, therefore, is capable of speaking on a continuum from hypo, which is mumbling, through to hyper, which is clear speech, and then the sort of normal and mid-range. And so here are some sort of measures. And what I'm just going to draw attention to, for example, is that on the results for the, we can see here things like the mean word durations in the hyperspeech are longer, and the mean sentence duration is longer, surprise, surprise. But particularly interesting for vowels is that the F1, F2, I'm assuming you know what formants are, the F1, F2 area is greatly expanded in hyperspeech. And that is an automatic consequence of the compensation in the control loop, right? We haven't trained this up to do this. This is a consequence of the closed loop control, which is a really interesting emergent property. And then for consonants, we've got a similar thing here, just a few measurements. And so a good one to look at here is the spectral center of gravity, which you can see shifts up from hypo speech to hyper speech. And that is a well-known effect. But again, this is an emergent property of the control structure. It is not being programmed in. So just to, let's hope all the audio works now, because I'm going to play you some examples just to prove this all works. So we've got examples here in English and in Italian. Mauro, as you might have guessed, is Italian, so that'll be why. I'm going to play you some speech in with various disturbances. In this case, we've got noise. And you can see the signal noise ratios here. So let me just kick off by playing this one here. So I'm going to play some hypo speech. So this is, you might think, why bother with this, but it's just proving the point. So we've got now synthesized mumbling, 1 dB signal to noise ratio, and you can hear the synthesis. This is HMM synthesis embedded in speech shape noise. So A, I hope you could hear there was something, and B, I'd be amazed if you could figure out what was said. So now I'm going to switch to this one and play the hyper. So the exact same sentence, but more importantly, the exact same signal to noise ratio. So this speech you're about to hear is not louder, okay? It's just clearer.
Box was thrown beside the park crowd.
You may well have got that, and I'll play it again.
Box was thrown beside the park crowd.
And if I put that up, you will now be able to hear it very clearly, of course.
Box was thrown beside the path front.
So I'll play the others since we're not constrained by time. So this is car noise now. Now this is seriously bad signal to noise ratio. So this means the speech is under the noise. And this is a female voice speaking Italian, but mumbled. And now the hyper articulated. And again, this is not louder. You might think it's louder. You might perceive it as louder because you can understand it, but it is not louder. And so she was saying that, and I know no Italian, so you may know better than me what that was. Okay, so hopefully you were able to perceive those and observe that the consequences of that architecture and the closed loop control and targeting the optimization on perception, it's possible to generate interesting behaviors from in speech. Right. So if Felix is happy, I will spend another just 5 minutes on this last issue, which is the usability one. Good. That was a moment to stay.
I'm happy. Mm-hmm.
All right. Good. Okay.
Quiet is consensus.
Yes, indeed. Thanks. All right. So what we've got here then. So this was the final slide line on that slide where we're looking at the state of the art. So where I mentioned that usability appears to be an issue. So what am I talking about here? So there's a graph that was given to me by a pal from SpeechWorks, actually, Mike Phillips, quite some time ago, which I've always liked, which is to do with usability. And usability of systems is something which I think is really important and is coming to the fore because we're now getting systems out there in the real world. So usability is something we obviously need to be concerned with. So Mike's graph, usability is on the vertical axis, as you can see, and then we've got flexibility on the horizontal axis. So in the bottom left-hand corner, we have systems, spoken language systems, which are not very flexible and therefore not very usable. So some of the early work on structured dialogue, just very small vocabularies. You had to learn a simple syntax, for example. You couldn't do very much. It wasn't very flexible. You could do some things, but and you had to learn it. So it's not very intuitive. So that's sort of the bottom left-hand corner. Top right, of course, is where where the famous human level capabilities are. Spoken language of the human being, of course, is very flexible, and therefore we can do lots and lots of things, incredibly usable. And what Mike Phillips pointed out, which is interesting, is we're on a trajectory, right, from bottom left to top right. And one of the things that Siri showed us when Siri suddenly appeared in 2011 is if we add some natural language processing and a bit of dialogue, then we become much more flexible, and therefore we can do many more things. And that's been demonstrated by all the apps and skills that are available for things like Siri and Alexa. So that's great. So we're on the march. We're going from bottom left to top right. And so what is the trajectory? And so this was Mike's suggestion, which is, you'd expect maybe over the years, it'd be nice if I could put dates on this, right? And say, okay, so we're 3/4 of the way, getting most of the way up to human. But this is Mike's graph. Whoa. And he was pointing out something which I've actually separately got experimental evidence for, which is that actually, as you make systems more flexible, we seem to get into a kind of weird state of affairs where usability plummets. And what this seems to be about is that users suddenly don't know what to do anymore. They know it's not a human, so they know they can't ask anything, or they can't just have a conversation. But what can they do? And so there's this kind of area of uncertainty, and I call this the habitability gap. Which is a term now which seems to have taken off. So it's not my term. I borrowed it from HCI. It's a well-known term in HCI. But I think it's an interesting phenomenon. So if you remember this, those early models on the left there, which were not very flexible, not very usable, essentially there's behaviorist, stimulus response. Backwards and forwards, very simple idea. And as long as the user knows that, it's habitable. And then, of course, we've got the human up there with this beautiful coupled system. And the habitability gap is a bit like this, where we've got one partner's powering along and the other one is being dragged along on the ground. It's fallen over. And so I think we've got an interesting problem here. Now, some of you might be thinking, hold on, I recognize this curve. And anybody who's into robotics will be saying, I've seen this before. This is this curve, and here it is. This is the famous Uncanny Valley. So if you haven't heard about this, the Uncanny Valley is basically saying that if we have robots on a continuum from industrial machines on the left to humanoid robots on the right, then we've got the vertical axis, which is, it's labeled a familiarity here, but the official term is affinity. Then as robots get more and more human-like, people start to like them, the fancy toys and what have you, until they get so quite close to human, and then people have an extreme negative reaction, and that's that big drop. And that's known as the Uncanny Valley. So it's not just that people find them unattractive, it's they actually petrified and scared and have an extreme negative reaction. So I could talk a great length about this, but I actually have, there's a lot of research in this, but nobody had ever modeled it mathematically until I came along about 10 years ago. I got interested in this because of Mike Phillips' graph, and tried to come up with a bit more of a mathematical explanation, a quantitative explanation, which he did. So I've got this Nature paper called A Bayesian Explanation of the Uncanny Valley Effect. And this makes some predictions, which was sadly lacking. It tells us some really interesting things here. It tells us the maths tells us what the source of the dip is. And more importantly, it tells us how we should overcome it. So I don't have time to go into this in great depth, but let me just give you the sort of punchlines, which is, in order to avoid the uncanny, we need to align affordances. So affordances is a sort of nice technical word, which is when we're interacting with something, it's what that thing affords us, how we're interacting with it. And the source of the uncanny valley, according to the model, is when we've got misalignment between the different ways in which we're interacting. So in a nutshell, if we're wanting to interact with a robot, especially by speech, what it looks like, what it sounds like, what it appears to be able to do, and what it appears to know, all have to be lined up. And if there's some sort of disassociation where what it looks like and what it appears to be able to do and what it seems to know are all wildly out of kilter, that is, the model says, is going to lead us into the uncanny valley, and people just won't know what to do. That's what the model predicts, which is really, really neat. So that has some immediate implications, which is, not if we need to align these things, well, what a robot looks like, we've got some control over. What it sounds like, you'd think we'd have some control over, but most people don't pay any attention to that. What it can do is mostly what roboticists are concerned about. And what a robot knows, that's a bit of an unknown. And the cognitive capabilities of robots are actually pretty limited. And if we need to align these things, we've got to align with the one with the lowest, it's capped by the one with the lowest capability. So if understanding is limited, everything else needs to go with that. That's a major, major consequence. And so the one that comes straight back home, there's lots of implications of that, but the one which comes right back into our field is that, so given that we don't know how to build robots with the same sort of cognitive capabilities and abilities, linguistic abilities as a human being, we certainly shouldn't give them human voices, which is, of course, exactly what we are doing. And then we wonder why people can't interact. Why is Alexa and Siri, why sometimes does it cause problems? It's got a human voice and it's not human. It's leading people down a garden path. And I'm just going to draw your attention. If you're interested in this stuff, there's a lovely book by a friend of mine, Bruce Ballantyne, which is just fun to read. And the title of the book is "It's Better to Be a Good Machine Than a Bad Person." Now, this is like a soapbox, a campaign here. And I have to say, I'm just to alert you to the fact that this is a minority view. Lots of people in our field don't like this whole idea, set of ideas. You know, they feel like, right, we've got to have human level performance. We've got to build the best speech recognizer. We've got to put the high quality synthesizer, and we'll just, you know, take the best robot we've got and we'll just throw all this together and it's going to be great. Don't worry. And what I'm saying is, hold on. There are some design principles here which we actually need to pay attention to. So this leads us into a bit of an issue, really, because spoken language interaction itself is founded on some pretty fundamental things, which I've tried to kind of hint at. Shared experiences, representations, priors. That's how language functions. So there might actually be a fundamental limit to what we can do with language between humans and artificial devices. So what does it mean to have language-based interaction with a mismatched partner? And there's a nice book here by Tom Scott Phillips called Speaking Our Minds, where he says the same thing, coming at it from the linguistics end. The assumption of continuity between a fully coded communication system at one end and language at the other is simply not justified. So again, it's in support of that Mike Phillips graph. We can't guarantee that there is a route from bottom left to top right. And I'm just going to illustrate that very quickly. This may be too complicated, but I'll draw your attention to it. I've published a paper which introduces some nice ways of visualizing a lot of these complex notions. And so without going into a separate lecture, this diagram here indicates two human beings interacting using spoken language, human-human languaging. So I'm not going to explain it, but if you look inside each of those agents, because there's two agents there, they've got representations of each other, and within that there's representations of each other. So this is allowing languaging. Languaging is defined by Tom Scott Phillips as ostensive, inferential, recursive, mind reading, essential elements of languaging. But these are matched. When we've got mismatched interlocutors, we've got the human on the left, which has all these recursive models, but the poor old agent on the right, we knows nothing of this. Nobody's programming a robot to have recursive mind reading. In fact, we don't even do much on the way of ostension, which is actually knowing that you're being spoken to. But what we do on the robot side, or the spoken language processing side, is we do build good inference models. But that's about it. So we've got this huge mismatch, and that's going to be a problem. That means we're not going to. So if you ask me on a bad day, are we ever going to have language-rich conversational interaction between a human being and an artificial agent? I would say no. But you can also catch me on a good day. Anyway, so a bit of light at the end of the tunnel here. We do have examples of mismatched interlocutors. So obviously adults and children communicate, and there's a big mismatch there. We have people in different languages and different cultures are able to interact, and people with, for example, ailments like inability to hear clearly and stuff like this, hearing impaired. So we have some examples. So will any of those examples help us to understand the kind of mismatch we have between a human being and an artificial agent? Well, I was suggesting that was good news, but here's the bad news. But these are all conspecifics. These are children are cognitively incredibly well-developed human beings, right? And even if we're used to talking to people in different cultures and language, we're all still human beings. So where can we look? And this is where we come into the animal kingdom. First of all, what on earth are animals doing? Where are our models of animal communication, which is the foundation for language? Nowhere. And what is it that people are doing when they're using language, which they do, of some kind, to interact, for example, with dogs? What's going on there? We don't know. And I'm suggesting these are places to look. And that is it. So sorry about the race at the end, but I wanted to complete the picture. So this is where I think we are. We have made the most amazing technical progress. We're very reliant, though, on huge data sets, and we're ignoring what I think are absolutely fundamental priors. We ought to be able to come up with more factored solutions. In other words, we ought to be able to break through this reliance on huge data. But if we're going to do that, then we might have, I've shown you some architectures which look like they might be able to do that. I forgot to say, by the way, our speech synthesizer is not trained on huge amounts of data. It just does that as an emergent property. But if we're going to create usable systems, we need actual design principles. And there may be a massive mismatch between living and non-living agents, which means that, that languaging is fundamentally limited anyway. So the original question was, what's left to be done? And the answer is a lot. There's a lot left to be done, but maybe not in the directions that a lot of people are going. So if you're interested in any of that, there's a book called Robots That Talk and Listen by Judith Markovits, and there's a chapter in there that I wrote called From Talking and Listening Robots to Intelligent Communicative Machines. Unfortunately, you'd have to buy the book, but if you're interested, send me an email and I'll send you the PDF. You can also find stuff on my webpage. And I just want to finish by pointing out that here at Sheffield, we actually have a Centre for Doctoral Training in Speech and Language. So we're taking in cohorts of PhD students every year for 5 years. We're just taking in our third cohort now, building up a big community of PhD students in speech and language, straddling the speech research group and also the natural language processing group at Sheffield, both of which are significantly sized groups. And that's it. Thank you very much. And thanks for allowing me to go on a little bit. It was nice to get to the end without having to short circuit it.